So here's another example that we're going to have a look at. So we're asked to find the output voltage, and we have, again, a op-amp amplifier circuit. The main difference here is that there's two different voltages connected to this non-inverting terminal. And actually analyzing this one here, you might just need to pay a little bit of attention. That's pretty much the only tricky thing here. But anyway, let's run through our steps. So first of all, we need to make sure that we have negative feedback. And I look at this circuit and I see, yes, there is a negative feedback path. So our output is connected through R4 back into our inverting terminal. So it's always the inverting terminal that we're checking for. So yes, negative feedback. Therefore, we can proceed with this method. So we will assume equal voltages. So I'm going to call them VP and VN. So assume VP is equal to VN and IP equals 0 equals IN, where these are the currents that flow in to the op-amp terminals. So those currents are 0. All right. Then step 3 is solve the circuit. So analyze it with those assumptions baked in. Now, the only thing that might be a little bit tricky here is actually how do I solve for VP? Because once I know VP, then it's straightforward from that point onwards. And this one here, just in case this connection of two inputs here is a little bit confusing, I'm going to redraw this in a way that might make it a little clearer. So for clarity, redraw the circuit at the non-inverting input. All right, so I have a voltage V1, and another way of saying that is that I have a voltage source that connects to ground that produces a voltage V1. So I can replace what was a node with a labeled voltage. Whenever we have a node with a voltage labeled on it like that, we mean that's a voltage with respect to ground. So on the input side here, we can think of it as it's a voltage source. That then runs through a resistor R1, and then we get to our node that runs off into our op-amp, and so that was VP, the voltage we're trying to solve for. But the rest of my circuit comes back. There's a resistor here, R2, and then it runs into a node with voltage V2. And the other way to think of that, well, I have a voltage source of voltage V2, and that connects to ground. So I'm just going to make this wire a bit longer. So that connects down to ground. So now I've made it a little more explicit and I have a complete loop. So I can easily apply KVL to this loop. So can apply KVL to this loop. Or you can solve it other ways as well. But let's actually go and write down what will be the current around this loop. So using KVL, so I'm going to have a current here, I, and I'll start in the bottom left corner and write down the equation. So I'll have negative V1 plus R1 times I plus R2 times I plus V2 is equal to 0. And this is why it was important to pay attention, because you notice I actually end up with different signs here for my two different voltages. As I proceed all the way around that loop, those are the signs that I encounter as I approach those voltage sources. So this is why this one was a tiny little bit tricky. So continuing onwards, we want to know, what is the current. So let's solve for the current. So I'm going to collect like terms. So bringing all the terms involving the current together. I'm going to bring my voltages to the other side. So that will be V1 minus V2. over to the other side, which tells me that the current V1 minus V2 divided by R1 plus R2. All right, but I actually want to know what is the voltage. So one way to calculate what that voltage would be is to start from the reference node and then just follow any path through the circuit until I get to the point that I'm interested in, and I just accumulate all the voltages along the way. So I'll do this in the direction of positive current, so that I am making sure I don't have to do anything tricky with the signs. So basically my voltage VP is going to be, as I go from ground, I get to this first node here, I gain a voltage of V1. So this first node, when I say first node, I mean this highlighted point here. This first node is V1 volts higher than ground, so I have that. But then I will have a loss of voltage due to the current flowing through that resistor. And the loss will be I times R1. So that will be the actual voltage at my source VP. So that's the reasoning that I use. So I gain from the voltage source and then I lose because of the current flowing through that resistor. So I can substitute in what I know about I1, or just I should say, what I know about I. So that is this, R1 plus R2 times R1. And can I simplify that any further? No, it's pretty much how I would leave it. You could potentially, I could probably put that first term over a common denominator with the others. So let's just see how that's going to look. If I write V1, R1 plus R2 divide R1 plus R2, so this is just the first term, minus this. I'll bring the R1 inside, so it becomes V1 R1 minus V2 R1 divided by the same denominator. So I have that, and this will clean up a little bit. So bringing all of this together, I actually have some terms that are going to cancel. So V1 and R1 here are going to cancel, and here's what I'll be left with. V1 R2 plus V2 R1 divided by R1 plus R2. Okay, this is my voltage at the positive terminal. So let's go back to what we were trying to do. If I know the voltage at this terminal, then because of the behavior of the op-amp, I therefore know the voltage at the other terminal. So we're pretty much there as far as solving this circuit. So let's do KCL at the node labeled Vn. Let's just draw it up here so I can see it on my screen. So, in fact, easier way. I'm going to redraw my circuit just a bit further down so that you can look at it while I'm writing out what I know. So let's just take that. Here was our circuit, and let's go and do KCL at node Vn. So as usual, current's leaving, it's Vn minus 0 to the left divided by R3, draw that clearly, R3, and then current's leaving to the right would be Vn minus V out divided by R4 is equal to 0, and we can substitute what we know about Vn because we just calculated it here. So substitute Vn equals Vp equals the thing that I highlighted. So subbing that in, I'll collect like terms first and then I'll sub it in. So I'm going to bring the factors just because it's complicated. So I'm going to have 1 over R3 plus 1 over R4 times Vn is equal to V out over R4. Okay, now we'll substitute it in. 1 over R3 plus 1 over R4 times Vn, which is V1 R2 plus V2 R1 divide R1 plus R2 is equal to V out over R4. Okay, can we simplify this? We can take the left-hand factor and we can put that over a common denominator. It's fairly much just aesthetics at this point, but let's see if it gets any simpler. So putting that one over a common denominator would give me R3 plus R4 divided by R3 R4, and that is then multiplied by all of this, V2 R1 divided by R1 plus R2 is equal to V0 on R4, and R4s will cancel there, and we're pretty much done. I don't think I can simplify that any further, so I'm just going to leave it as this. So V out is R3 plus R4 divided by R3 times V1 R2 plus V2 R1 divide R1 plus R2. So I guess taking a step back, like what is the purpose of this, or what does this tell us? Basically, if we had an op-amp circuit like this one here, and we wanted to use it to combine together, to mix together these two different signals, right, two different voltages, so to mix together V1 and V2 in some way to produce an output voltage, and we also want to amplify them, then here is the design equation that describes that relationship. So we choose values R1, R2, R3, and R4 in order to get the correct amount of mixing and amplification that we want for a certain application. So this is then I guess we go through and pick some values in order to achieve the required characteristics. So if you want, so a larger contribution due to, let's say due to V1, you want a larger contribution. Well, you could achieve that by having a larger value of R2, right, and relative to R1, and therefore the terms here will be combined in such a way that there is a greater contribution due to V1, or whatever proportionality that you actually choose. So that's where these sorts of things would actually come in handy.